Hello, Physics 182 students again. This is Professor Jeff Wilkerson at Luther College. For those of you who might not be Physics 182 students and happen to stumble across this and are watching it, now what we're going to do is we're going to calculate the rate of heat flow via conduction between two nested spheres. And I've drawn the situation for you here on the board. And I know what you're saying. You're saying, those don't look like spheres. It's kind of flat there and kind of bulbous there. Yeah. Think about turtles chasing cars. Turtles chasing cars. Anyway, what we've done in this experimental setup, what we're going to try to calculate is we have, imagine you're doing an experiment and you've got a sample inside here and you need to hold that sample at some low temperature, maybe liquid helium temperature. Okay, so this could be a real solid state kind of experiment, a dark matter experiment, some kind of experiment that you're doing. And this needs to be at some fixed cold temperature. And you've got the room out here. And so you've got a fixed room temperature out here. And you're asking the question, what's the rate at which energy gets conducted from here to here? If you take these two nested spheres, outer sphere I called R2, inner sphere I called R1, and you take those two nested spheres and you fill the space between them with some foam. I've called these steel spheres. That doesn't matter. Okay, what matters is that what the conductivity of this foam is, because that's the material through which the heat is being conducted, is that foam. So we need kappa of foam is what we really need to be worried about here, the conductivity of the foam. When we do this calculation, the steel doesn't mean anything to us unless we weren't able to fix this, for example, at a temperature, a cold temperature, and then we wanted to know how quickly that temperature was going to rise, and then we would need to say, oh, the Q that's going in here is raising the temperature of that inner sphere, and you would have an MC delta T kind of thing, and you could calculate delta T, but that's a complex problem, a fun problem. It's an interesting problem that maybe we can tackle down the road here just a little bit to say once that temperature starts changing, then the rate of conductivity starts changing. And you've got a little bit of a feedback loop there that you got to worry about somewhat. So what we're going to say is we're going to say the power, the rate at which energy, that's dq dt, right? That's the rate at which energy is being transferred from the outer sphere to the inner sphere, is going to be equal to the integral of, well, let's do it the other. Let's say it's kappa times 4 pi r squared. Okay, that's that r right here is some arbitrary r. So we're working in a coordinate system. We've got a coordinate system set up where it's really a spherical coordinate system, and the origin is right there, and that r is some r vector across here. Okay, so it ranges from R1 to R2, from the inner sphere to the outer sphere, and so we've set up a coordinate system where we've got a spherical coordinate system, and that's the radius r in our spherical coordinate system right there. And r is a variable. It varies from 0 to R1 to R2 to infinity if you just keep going on out that direction. So that's the first thing we've done, is set up this coordinate system. That's the first thing we should always do, is clearly identify our coordinate system. Okay, so we've done that now, and we're going to say this is 4 pi r squared is the area of a sphere of arbitrary radius r in our coordinate system, and dt dr is the temperature gradient across there. So that's the conduction, that's what we've written down as conduction, with an area here, and this dTdr, our expression for the rate at which heat gets conducted. Now, what makes this problem interesting for us is this r. A lot of things make this problem interesting for us, but one of the things that makes it interesting for us is that this r is a variable. Okay, as you move, if you're asking how much heat, what's the rate at which heat is flowing from the hot sphere to the cold sphere, r is not fixed. You can't just stick an r in there like we will do in class, or we did in class, depending on when you're watching this. A pane of glass, you've got some fixed area right here, and you just plunk that area in. And then you've got some fixed temperature gradient across there and some fixed thickness, and all of this falls out and it becomes an algebraic expression, and we just plunk the numbers in there. That is not the case here. Okay, that's not what's going on because this R is variable across there, and we have to deal with that variability in R as we move across. So we're going to say we're going to separate these variables out a little bit, and we're going to say that P, the power, the rate, times 1 over R squared. So let's move this R squared over to the other side and say P times 1 over R squared dr is equal to kappa of the foam, that's the conductivity of the foam, times 4 pi dt. Okay? Everybody with us so far? Take a second to look at that. Make sure that you see what we've done here. We've sort of pulled the variables, separated the variables out right there. Temperature on this side, which doesn't appear, and 1 over R squared dr on this side. And we're going to integrate these up. So let's integrate from the outer sphere to the inner sphere because we know that's the direction that heat is flowing from hot to cold. We don't know that yet because we haven't talked about entropy yet, but we will, unless depending on when you're watching this, we will talk about entropy very soon, and we will understand why heat flows the direction that it flows. But right now we know it flows from this way, so we're going to integrate from R2 to R1. Let's integrate this direction. So on this side, we'll do an integral from R2 to R1. It doesn't matter which direction we do the integral. We could have integrated from R1 to R2. The minus signs are going to work out. If we're careful and we do everything correctly here, our negative signs will take care of themselves, and we're going to get the answer that we get. But we're calculating. Understand what we're calculating here by doing the integral this direction is we're calculating the rate that energy is flowing from here to here. So if we get a positive number, that's going to tell us that the energy is in fact flowing from here to here. If we calculated it this way and calculated the rate that energy was flowing from here to here, and we got a negative number, that tells us, we chose the direction of the heat flow incorrectly, and the heat's actually flowing the other direction. So positive heat flow this direction is equivalent to negative heat flow that direction. So again, it doesn't matter which way we set this up. We're going to get the result we want to get, the result that's going to work for us, that's going to help us understand what's going on in our experiment here. Let's call it a dark matter experiment. In our dark matter experiment, no matter which way we set this up. But if we do the integral from R2 to R1, we better do the integral on this side. Notice that I've just written the integral sign so that the constants are outside the integral. From TH to TC. Okay? So that's what we got. So we've set our integral up there. This side, even I can do that integral. This side is going to look like the kappa of foam times 4 pi times TH, TC minus TH. After all that yelling at you about being careful with your negative signs of which direction you're doing integrations, I almost did that incorrectly. Oh, I hang my head in shame. So anyway, on this side, the integral of r to the minus 2 dr is r to the minus 1 divided by that 1 more power, minus 1. So this side looks like negative p. Let's just go ahead and do it that way. Let's just keep that negative sign comes from the dividing by the negative 1, the 1 more power. Negative p times 1 over R1 minus 1 over R2. Okay, so I think we've got that where we want that to be. So let's pull this up. If we pull this up, we're going to get R2 minus R1 divided by, so multiply this side by R2 over R2, and this one by R1 over R1, get our common denominator. And we're going to end up with R2 minus R1 over R1, R2. But now let's suck that minus sign inside there and swap those around. So this is going to be P times R1 minus R2 over R1, R2 is equal to kappa of foam times 4 pi T sub C minus T sub H. Okay? Now, remember what we were interested in. We're interested in the rate at which heat's flowing in there. We're interested in that power, so let's solve for that power. And the power is going to be R1, R2 times kappa of foam times 4 pi divided by R1 minus R2 times T sub C minus T sub H. Okay? If we swap the order of these, that gives a negative sign. We can swap the order of these and get a negative sign too if we want to do that. So let's do that. Let's go ahead and swap the orders of the order of these variables and say this is equal to K of foam 4 pi over R2 minus R1 times T hot minus T cold. That's a positive number. That's a positive number. Now that was a negative number. That was a negative number. It didn't really matter. But now we've got everything in there in terms of that difference is positive, that difference is positive. And that's the rate at which heat is flowing across the foam that's separating our two spheres there. So take a look at that calculation. I left the R1, R2 out of there, right? When I made that extra step that I didn't need to make. Always making an extra step you don't need to make always leads to trouble. So there you go. That looks better. So that's the rate at which power is flowing across that interface. That's the rate at which power is flowing into our inner sphere. If this is a dark matter experiment where we're trying to keep this cool with liquid helium, that tells us the rate at which liquid helium is going to boil off and whether we can do this or not, or whether we're going to lose the liquid helium so quickly we can't possibly do the experiment that we want to do. So it's an interesting calculation to be doing. We'll look in class a little bit and then maybe set this up for you to do as homework, a possibility for you to do an example of this as homework, maybe in a simplified form. We'll do that. We'll look at this. Now you take the foam out and then ask the rate at which radiation is heating the interior here. Okay, that's your next step. If you want to limit the rate at which heat's flowing to the interior, take that foam away and have the only mechanism for heat transfer to be radiative, and so we'll calculate the rate at which radiative power is radiant energy is being radiatively transferred across that gap, and to see how we can do that direction. So that's our example. Let me know if you have questions about it, and we'll see you soon.